first of all, thank you for the invitation and for organizing this event. Really, really good to be here and see all of you. Let's talk about rocks. When we look at some of the studies that have been done to assess the CDR potential of enhanced weathering deployments, we are quite regularly confronted with very large numbers. We've heard them earlier today already. When we're talking about the global scale, talking about gigatons, and even at the scale of individual countries, we often see numbers in the tens of millions of tons of removal potential every year. But when we then dive a little bit deeper into the requirements to achieve these removals, and particularly when we look at the availability of feedstock, the picture becomes quite different. So for now, essentially all larger enhanced weathering deployments are working primarily with existing byproduct streams from quarrying, from mining operations. And these feedstock streams are very limited, as this study, for example, shows. So when we take these 3.7 million tons per year of waste fines with suitable composition that are produced in the UK, and based on that, calculate a CDR, an approximate CDR that could be achieved, that is about an order of magnitude below what we saw in the previous study. So where does that lead us? Well, essentially, it means that if we want enhanced weathering to really play a significant role in our fight against climate change and be a significant component of any CDR portfolio, then we will need mining, we will need additional and dedicated production of feedstock material. And that is obviously something that for, I'm assuming quite a lot of us, is also a bit of a scary thought, because it comes with some very obvious challenges. So the first one would be very long permitting timelines for any new quarrying operations, especially here in Europe or in North America, where we're talking about up to a decade to even get a new quarry started. We would require a lot of CapEx to get these plants, these additional grinding capacities, for example, running, and the operations themselves would also require a lot of energy, and the processing and mining would cost money. So some very clear and large challenges that shouldn't be underestimated. But I would say that at the same time, there are also some major opportunities that shouldn't be overlooked when we consider that we in the future won't entirely rely on byproduct streams anymore, but can think about dedicated production of enhanced weathering feedstocks. And the main benefits that I see there are related to the direct and the targeted selection of rock types that are most suitable to enhanced weathering in their chemical and neurological compositions, and oftentimes much better than many of the feedstocks that we are currently considering. So when we look at what sort of feedstocks are being talked about and written about, thinking about enhanced weathering and the scalability of this method, we have maybe three different terms that are being thrown around quite a lot. First one being silicate rocks. That's obviously a very broad one that can be anything from sandstone through a granite to a basalt or even peridotite. So that doesn't really tell us much. There's olivine, which usually is being used when we're referring to ultramafic, so olivine-rich rocks, because people don't want to talk about dunite or Harzburgite for some reason. And then there's basalt as one of the omnipresent terms, and there was a really good talk by David Manning just 2 days ago at the ERW 24 conference at Yale, talking about just this and the nomenclature of different feedstocks. I really recommend reaching out to him if that's something you're interested in. But what I'm trying to get at is that really the current debate is circling around some very specific terms, and really limiting the number of different potential rock sources that we could and should consider when it comes to feedstocks for enhanced weathering. Because basalt, for example, we use it in a very broad sense, but it's actually quite a well-defined and narrow term. So using the definition by Lemaitre, we are talking about volcanic rock consisting essentially of calcic plagioclase and pyroxene. Polygon minor folds and minor interstitial quartz may also be present. And this is then defined either via the mode of mineralogy or the chemistry, depending on the rock type. This might be a bit confusing for the non-petrologists in the room, but essentially what this gets down to, two different ways to classify it, either mineralogy on the right, or if that doesn't work, we use chemistry, so total alkalis versus silica on the left. And when we plot the fields which correspond to basaltic or basalt, in this case, we see that they only make up a very small portion of the range of mineral and chemical compositions that are realized in the natural world. Of course, this is a very abundant rock type, present essentially all over the world and in large quantities. But when we think about optimizing, especially early on in the early stages of scaling up enhanced weathering, we should not just be looking at what is the most abundant, but what is the best, especially when we have that chance of optimization through dedicated feedstock production. And the first step of finding this optimal feedstock, these rock types that are best suited for our purposes, is of course to define the requirements. So what are we looking for in our feedstock? In the end, it can be boiled down to, okay, we want it to be safe for human health and the environment. We want it to sequester a lot of carbon, and we wanted to sequester that carbon, that CO2 as quickly as possible. In detail, there is, of course, a few more requirements that then express themselves in the chemical and mineralogical composition of that feedstock. So looking at the chemistry, we obviously want our rock to be rich in calcium, magnesium, and potassium, maybe sodium, although there's some debate to be had about that, just to ensure that we have a high CDR potential in the feedstock. At the same time, low concentrations of potentially toxic trace elements. And then we already talked about the potential side benefits of this method. Relevant plant nutrients are an added bonus, although plant availability in some of these is a bit questionable, especially when we're looking at phosphorus, for example. I'm not sure that we have a whole lot of data on that just yet. And then there's some MRV related aspects also in the chemical composition. So when we think, for example, about a feedstock that is very high in harmless immobile elements that could be used as tracers for soil-based mass balance approaches, titanium, niobium, and the likes, that would be as well an added benefit. When we look at the mineralogy, then we obviously want this calcium, magnesium, sodium, potassium to be present in fast weathering silicate rocks or in amorphous phases. We really do not want any asbestiform minerals in there, which is, in my opinion, still an underestimated risk, because a lot of deployments and also a lot of academic studies are using metamorphic rocks, so metabasalts, for example, where we do have that risk. In addition to the asbestos problem, there is also a problem regarding silicosis, because we are usually working with these very fine-grained materials, so also something not to underestimate. And then there might be some not harmful minerals, but ones that could cause us a bit of headache when we think about actually measuring weathering and related element fluxes. These are, well, the obvious ones are the carbonates, but also sulfides and sulfates can cause some problems in that respect. Okay, so we can, I think, quite well define what we would like our feedstock to be able to do, what characteristics we would like it to have, but how do we get from this to then the actual rock type that we'd like to use, and in the end, the deposit that we'd want to mine to produce that feedstock. I think a pretty good starting point is always publicly available databases, and one such database is the GeoRock database, which contains a whole lot of whole rock geochemical data, but also mineral geochemical data on different primarily igneous rock types. And what I did here, I've plotted a range of different rock types from intermediate to mafic to ultramafic, looking for now just at two of the key criteria that we defined earlier. So on the x-axis, the CDR potential versus then on the y-axis, the nickel content. These are, to be honest, two of the main criteria that we should be looking at in many instances. And well, also you just got to start somewhere. When we think about how to use these two criteria now, or how to define our requirements regarding these two, we can, at least here in Europe, actually set a pretty clear cut when it comes to nickel, because we are in the lucky or unlucky, depending on how you look at it, situation that we do have quite clear regulatory limits for many agricultural inputs. value that I used here, the 120 ppm, that's for us in Germany. At the EU level, we're at 100 ppm. There are, of course, other parts of the world where these regulations are not in place and where other feedstock materials are being used. And there's probably also debate to be had about the reasonability of these limits. But for us, this is the operational constraint. Anything above that is out. On the CDR potential side of things, we are, of course, a bit more flexible, hence the dotted line. But our preliminary economic assessments of different scenarios have quite clearly demonstrated to us, I think, that when you're dealing with feedstocks with a total sequestration potential significantly below 0.3, you are going to run into problems when you try to implement enhanced weathering. At least here in Europe, that's going to be hard to do that in a way that is financially sustainable, at least with the current MRV cost structures that enhanced weathering companies have to deal with. So really, we're looking at that bottom right quadrant for the rocks that we would consider suitable or very suitable for operations. Now let's look at a bunch of different rock types within that context then and look how they perform, starting, of course, with basalt. And we see that even though this rock is actually quite clearly and narrowly defined in its mineralogical chemical composition, as we saw earlier, it still spreads quite a wide range in this plot of nickel versus CDR. And we see that quite a large proportion of these points actually plot outside of that bottom right quadrant. So a not insignificant amount is showing nickel values that are much higher than our regulatory limits. And quite a few basalts, also just from their carbon capture potential, are not really attractive, at least from an economical standpoint. So I think the important takeaway here is basalt, not all basalts are the same, and not all basalts are actually suitable for enhanced weathering deployments. Let's look at another rock type. So showing here again the task diagram with the QAPF, a basanite, which is another volcanic rock type, which is more undersaturated in silica than basalt and generally has slightly higher alkali contents. It's a bit rare, obviously, but it's still globally present and relatively widespread. And when we look at how this rock type performs, we again see that quite a bit of that plots over our 120 ppm of nickel, but those points that plot below it show a notably higher average CDR than we would see for basalt. So essentially, we're just moving the whole thing a little bit to the right. And when we take it a bit further to the extreme in regards to silica undersaturation, looking at fluidites, so these are generally showing silica contents below 41% and often very high contents of sodium and potassium. These plot even further to the right. So we see similar distribution with regards to the nickel, but even higher CDR potential. So these are just some examples, obviously not exhaustive in regards to the rock types that are considered and plotted here. I just wanted to give you that quick insight. And now really quickly, just talk about how that could translate into practice. So we've also been doing some of our own, sorry about the formatting, that's I think a Google Sheets or Google slide issue. We've been looking at some of the rock types or feedstock types that are available currently within Germany and some of our neighboring Eastern European countries. And really, there's no big surprise here after we've looked at the larger GeoRock data set. These are all available byproduct streams from existing quarries. And we see these results essentially confirming what we saw earlier. Obviously, the more intermediate composition rocks, the granodiorite, andesite, significantly lower CDR max. But we also see the basanites and the fluidites plotting consistently higher than the normal basaltic rocks. In regards to the nickel then, and that goes for some of the other heavy metals as well, we see generally similar or lower values as for the basaltic rocks. We have relatively high titanium and maybe more interestingly, very high niobium contents, so potentially suitable in the right setting for MRV via soil-based mass balance approaches. And when we think about the co-benefits, significantly higher phosphorus contents than your average basalt would show. So some quite interesting rock types there, I would say, these highly silica undersaturated alkaline volcanics. And now that we have identified these as potentially very suitable, very favorable rocks for enhanced weathering, we can go that next step and think about, okay, yeah, where are we going to find these? And we are in luck in the sense that these sort of exotic rocks, but still widely occurring, are limited to very specific geotectonic settings in their occurrence. So when we think, for example, about, I mean, we're talking about Europe here, so let's look at Central and Western Europe for now. We can see that these alkaline volcanic rocks occur primarily within tectonic depressions, so specifically within rift systems. And when we want to conduct active exploration for optimization of our enhanced weathering operations, for identifying the ideal feedstock, this already narrows the regions, the geography of where we have to look quite significantly. And once we have these regions identified, which are suitable from a geological point of view, it's much easier to then conduct regional sampling campaigns and actually identify and get down to the source. And I do have some conclusions. Yeah, it's plural, which some of these are very basic, and I think I said some of them already in the previous slides. So first of all, not all dark volcanic rocks are basalts. Not all basalts are suitable for enhanced weathering. And there are actually quite a lot of rock types out there which might be significantly better suited for enhanced weathering than basalts. And I think it's really important to keep in mind that if we actually want to get enhanced weathering to the scale that we are advertising it at, and every single one of the larger review papers that talks about the potential implicitly takes into consideration that there will have to be a significant expansion of mining activity. Not a lot of them talk about that very actively, some do, but it is something that we need to think about, and we also need to see the opportunities that come with that with regards to specifically feedstock selection, because we won't have to rely anymore on the rock types that the construction material industry considers suitable for their causes, because those criteria are very different and often actually contrary to each other. And then maybe on an even more general note, we kind of, in the enhanced rock weathering space, have to not just consider the weathering and how to enhance that, but also think about the rock behind it a little bit more. And I feel like some more petrology and some more mineralogy would do a lot of these studies, and also some of these deployments really good, because that's fundamental controls of essentially everything that happens afterwards. And I just want to give a really quick shout out to some of the studies that have been doing a really good job at that. So starting with the paper by Amy Lewis in 2021, but more recently also Liam Bullock and Emily DePass have been publishing some really good work in that direction. And then of course also David Manning with his talk at ERW 24. Can really recommend talking to him as well if you're interested in that topic. And yeah, with that, I'd like to thank you all very much for your attention.